Hi, welcome back to my YouTube channel. My name is Abdul Wahab Ademoku and I'm a college maths instructor. In today's video, we are going to look at how to diagonalize a transformation. And this is one of the videos, one of the several examples in the video series on this channel on linear transformation and linear algebra in general. If you haven't watched the other videos, kindly go through the channel and go ahead and watch those videos as well, right? The link will be in the description for the previous videos if you're interested in looking at other examples in this on linear transformation. So let's just get right into it and look at how to diagonalize this particular transformation. As you can see, this transformation is from r cube to r cube, and the transformation is given, right? And we are asked to diagonalize this if possible. So this is an endomorphism. As you can see, it is from r cube to the same, from one vector space to the same vector space. So it's an endomorphism. And then we are asked to look for the characteristic polynomial, the eigenvalues and eigenvectors. And once we find this, we can now use this information to diagonalize the transformation. So let's see how we can do this. So the first thing that we need to do is to find the matrix of transformation relative to what? Standard basis for R cube, right? And this is extremely important. So what are the standard bases for R cube? I think we have mentioned this in the previous video, so make sure you go ahead and watch that. This is basically E1, E2, E3. Right? Where E1 is the vector 1, 0, 0, E2 is the vector 0, 1, 0, and E3 is the vector 0, 0, 1. Right? Okay. Now we need to look for the matrix of this transformation relative to this standard basis. Right? So what we do is we find the transformation of these vectors. Right? And we're going to use this result to characterize the matrix. So how do we do this? So this means that what your x is 1, your y is 0, and your z is 0. And when we substitute that into this transformation here, right, what does this give us? 2 times 1 plus 0 for the first component, and 0 minus 0 for the second component, then 2 times 0 plus 4 times 0 for the third component. So that will give us basically 2, 0, 0. For the second one, we do the same thing here, where y is 1 and the rest, and x and z are 0. So that will give us 1, 1, 2. And finally, we look for the last one when z is 1 and x and y are 0. So we have this. Okay. So just make sure you go through that to be sure that this is correct. Now that you have this, so the matrix of transformation is quite easy. It's just that we write, because we're using standard basis, it's quite easy to write. Like I said, I'll also be making videos on other examples where it's not so straightforward. Okay, so this can be written as what? 2e1, 0e2, and 0e3. The same thing here, 1e1 plus 1e2 plus 2e3. And the last one, 0e1 minus e2, 1e2 plus 4e3. Now we are going to write this these coefficients into the column as a column vector for this matrix. So that's going to be 2, 0, 0, and the next one is 1, 1, 2, and the last one is what? 0, minus 1, 4, right? Or basically, you look at this vector and you write it as a column vector in that matrix. So that is how we get the matrix of transformation relative to what? Standard basis. Now that we have this, the next thing is to find the characteristic polynomial. So that will be the next step. And how do we find this? This is defined as what? dt, right? And how to do this is basically, this basically means we need to take the determinant of this matrix A minus Ti. And what this means is just the determinant of the same matrix, but we are subtracting T from the diagonals of this matrix. So this is what we need to do. Okay. Now, what happens here is how to find the determinant of 3 by 3 matrix. So as you can see, we use the easiest row or the easiest column. As you can see, this is the easiest 1, this column, right? So we use that, which means the first entry, 2 minus t, multiplied by the determinant of, when we close out the row and the column this entry belongs to, that would give us the rest. Sorry, you have -1 here, the rest of the entries of the matrix we need to find a determinant of. Now from here, how to find the determinant of 2 by 2 matrix is just basically multiply the diagonal minus the other diagonal. So that will give us 1 minus t times 4 minus t, then minus 2 times minus 1, which is -2. So this is what we need to simplify. Okay, so let's continue this. So that's 2 minus t. We need to expand this. So how do we expand this? This is just 1 times 4. So 1 times 4, 1 times minus t, 4, t times minus t times 4, and minus t times minus t. So 1 times 4 is 4, 1 times minus t is minus t, then minus 4t, then plus 4t squared, then minus times minus 2, that's plus 2. So we just basically have this. So let's quickly go through this simplification. We have minus 5t plus 6. And then what we do here is we kind of factorize this. So this is quadratic expression. To factorize this is just t minus 2 and t minus 3. So you could try to figure that out, how we got t minus 2, t minus 3. It's not so difficult. If you are requiring a video on how to do this, please, you can comment below so that I can make a video on how to simplify quadratic expression. So now with this, we can switch things out so that the first factor will now be t minus 2, t minus 2, then we have t minus 3. So the reason why we're doing this is because we want to square this factor. Now, what does this mean? This will now help us to get the eigenvalues and eigenvalues for this transformation using the characteristic polynomial. So this is your characteristic polynomial, right? Now, what we do next is, so let's just move back up a little bit. So what we do next is we find the eigenvalues. So that's the third step, the eigenvalues. So we know that what the characteristic polynomial is this. So what does that mean? So the eigenvalues are the values of t that would be the root of this characteristic polynomial, which basically means the values of t that will make the polynomial to be 0. So if you do that, you'll see that what t minus 2 squared, t minus 3 equal to 0, which means t is equal to 2 and t is equal to 3. But this is twice, right? We have a factor repeating itself there. Now, what this means is what? For t2, the algebraic multiplicity is 2. And for t equal to 3, algebraic multiplicity is 1. So what are we expecting? There's a concept called geometric multiplicity. We are expecting the geometric multiplicity of this to also be 2. And we're also expecting, so this is expectation. If at all this matrix can be, the matrix of transformation can be diagonalized, it means that what this must be true, that the geometric multiplicity must be equal to the algebraic multiplicity of each eigenvalue. So we are expecting this to be 1. I think we won't have problem with this one because once you have algebraic multiplicity of 1, you are sure to have a geometric multiplicity of 1. But what you're not sure of is the first one, when t is 2, whether the geometric multiplicity will be 2 as well. So now let's go into that. So that's our next step. So the first step is to find the eigenspaces of each eigenvalue. So what does this mean? All right, so what does this mean? It means that we now put back this t into this polynomial, into this matrix, right? So we have to put t into this matrix. So for t equal to 2, what do we obtain? We have, there's 2 minus 2, that is 0. We have 1, we have 0 here. Here, 1 minus 2, that is minus 1. We have minus 1 here, we have 2, and then we have 2 here. Okay, so we said this is, if you're familiar with linear transformation, you would understand that this is the coefficient matrix of a homogeneous system. So what this means is if you have x, y, z, I've explained this in the previous videos. Please go back and watch those videos if you need more elaboration on this. So basically, this is going to be 1 times y, you have y equal to 0. For the second row, we're going to have minus y minus z equal to 0. And for the third row, we have 2y plus 2z equal to 0. So basically, y is equal to 0. For the other two equations, they are just the same equation. As you can see, if I multiply the second equation by minus 1, I will have y plus z equal to 0. And the same thing, if I divide the third equation by 2, I will get the same thing, y plus z equal to 0. And we got that what y must be equal to 0. Now notice that there's no condition on x, so it means x can be anything, right? So what does this mean? So from here we got that what y is 0, which means z must also be 0. So basically what we have now as our solution set would be x can be anything, y is 0, z is 0, which means we can take x out, and this vector 1, 0, 0 will span the solution space of this eigenvalue. So for this eigenvalue, for the eigenvalue of 2, so for the eigenvalue of 2, the eigenspace of this eigenvalue would be spanned by this vector. Now notice that what we only have one vector for this eigenvalue, which means the geometric multiplicity that we're talking about is 1 and not 2. This alone is enough for us to conclude that the transformation is not diagonalizable, right? So basically, that is it, right? So we can conclude here, T is not diagonalizable. And why? Because the geometric multiplicity of this eigenvalue 2 is not the same thing as the algebraic multiplicity of this eigenvalue. Okay. Now, for the sake of argument, you can go ahead. So just as an exercise for you, think about when t is 3. Try to find the solution space and the corresponding eigenvector. Right? As just part of the problem, but we know that we cannot diagonalize this transformation. Okay, I hope that is clear. Remember, this vector will be the eigenvector of this eigenvalue, right? Okay, so the same way, find for T3, find the solution space and also the corresponding eigenvector for that. Okay, I think that sums up this whole problem. So I will be uploading more videos, explaining this similar concept to you. So make sure you subscribe to the channel, like and comment whatever video you would like to watch, or send it through to my email for to request for a particular video that you would want to see on the channel. And then I would see you in the next video.